So here's a question for you, so please pause your videos after I stop talking. For the hydrogen atom, rank the energies of the states, 4s, 3d, 3p. So pause your video and figure it out, please. Okay, we're back. What's the equation for the energy? The equation is En equals minus 13.6 electron volts over N. Right? Or is it N squared? I guess it's N squared. Okay, so let's do it, right? So N, all right, so, okay, we can just figure it out, right? So if we have N equals 3, then we have En equals minus 13.6 electron volts over 9, and let's see if I have that. That's minus 1.51 electron volts. If we have N equals 4, E4 equals minus 13.6 electron volts over 4 squared or 16, and that's minus 0.85 eV. Now notice, remember, for hydrogen, the energy only depends on N, so I don't care if it's a 3D or 3P, same energy. Remember, that's only true for hydrogen. All right, so what's the answer? Ta-da! Okay, so there you go, right? Okay. Any questions? So this is obviously bigger than this. And yeah, that's all there is to it. Let's do another one. Okay. For the hydrogen atom, at what distance from the proton is a 4f electron most likely to be found? All right, so what we found, we said that R peak equals N squared A Bohr, but that's only true for L max, right? Circular orbits, right? Okay, so let's see, do we have a L max? Well, we have a 4f, so N is 4, so that means that L can be 0, 1, 2, 3. Well, what's F? Remember, SPDF. So we have the L max, right? Because the F state is the maximum angular momentum. So that means we can use this rule. And so what's the answer? Well, it's just 16, right? Because 4 is the N, so just 16. Yay. Okay. All right. Now let's talk about something called spin. I used this a little bit when we were talking about the shell model of the nucleus, when we did nuclear physics. I talked about spin, and I said we'd talk about it more now. Well, now is now, right? Okay, now, if you've taken Physics 220, you'll understand more than if you haven't. But I know most of you haven't, so I'm not going to give you a big Physics 220 lecture. I'm just going to get to the nitty-gritty, all right? Okay, I hope that's not so bad. All right, why am I showing you that again? I don't know. That's a review, I suppose. Yeah, go away. All right, so we want to learn about something called the magnetic moment. Okay, if we have a bar magnet, and this is the South Pole and that's the North Pole, there's something called the magnetic moment. So mu is called the magnetic moment. And it's just a vector, and it just points from the south to the north. And so it gives you the strength and the direction of the magnetic field, okay? So that's all you have to worry about. The magnetic moment, it's a vector. It points from the south pole of the magnet to the north pole, and it gives you some kind of indication how strong the magnetic field is. That's all you need to know. All right? Okay. Now, there's two ways. Oh, sorry. Get back. Okay, so in Physics 220, we learned how do you create a magnetic field? Well, one way you create a magnetic field is you have a wire. And what we learned is if you have a wire like this, it's like a circular wire like this, right? It produces a magnetic field that points up above it and points up below it. Okay? So basically what we learned in Physics 220 is that if you have a wire with a current in it, see I is the current, it's supposed to be uppercase I, right? If you have a wire with a current in it, you get a magnetic field that looks just like a bar magnet. It's exactly the same, all right? So this is just a bar magnet, that's a magnetic field, but then you can also get a magnetic field that looks just like that by having a current flow in a wire. Okay? All right, so there's your Physics 220. Now, think of an atom. You know, you have a nucleus and you have electrons orbiting it, right? Well, electrons, that's a current, right? And so the atom, guess what? When the electrons orbit the nucleus, they form a magnetic field, which is indicated by this magnetic moment, right? Points from the south to the north. So there you go, all right? So here, so the orbiting electron is a current loop, just like this is a current loop, right? Just like a current in this wire. A current loop generates a magnetic field with a north and a south magnetic pole. Okay, that's all you need to know for Physics 220, okay? Now, in quantum mechanics, you can calculate this magnetic moment in terms of angular momentum, okay? So here it is. You don't have to worry about how this came. Don't worry about it. It's not the important thing. But here's the formula. Okay, here's the formula. And then, right, so this is the vector, right? Vector, vector. This is the z component, so it has an L sub z. And then you substitute L sub z, you put an mh bar. And if you want to write it a little differently, you know, the m is the quantum number, so you can pull it outside, right? So you pull the m outside, then you have E h bar over 2 times the mass of an electron. Okay, that's all you need. Don't worry about it. Just, you'll see. All right. So now I'm going to describe a very, very famous experiment. Okay, so physicists knew that this was the equation for mu z. And again, it depends on the orbital quantum number there, the magnetic quantum number, m, all right? And okay, so what they did, they had an experiment, and they shot electrons, and the electrons went through a collimator. Basically, you know, if you just shoot electrons, they might go every which direction. But if you make them go through this slit, you know, then this stops all of the ones that aren't going in the same direction. Okay, so you put the electrons through a collimator, so you get this nice straight beam of electrons, and then you make the electrons go through a magnet. And so we learned in Physics 220 that magnets exert a force on charged objects, which change their directions. That's all they do, is change their directions. Okay, and then you have a collector plate, kind of like a screen, you know. And don't worry about this, just believe it. The force in the z direction equals mu z times dB dz, right? Okay, all right, so what we want to do is let's just consider an electron in the L equals 1 state. All right, if L equals 1, that means M goes from -1, 0, 1, right? 3 possibilities. Okay, well now, you know, you look up here. This is M. Okay, so there's going to be 3 possibilities, right? There's going to be -1, but this is a negative, so it's going to be +1, it's going to be 0, or it's going to be -1, all right? And remember, the force is proportional to this mu z, right? And there's 3 values of mu z, correct? And so there's going to be, what's going to happen to these poor little electrons? So here it is. You have a nice straight electron beam. Then it goes through the magnet. The magnet exerts a force. And guess what? You can have the m equals 1 go down. The m equals 0, there's no force, so it keeps going straight. M equals -1 goes up. Okay? That's the only thing that's important. Okay? You don't have to understand all these details. All you have to understand is that for L equals 1, there are 3 values of m, and therefore there are 3 values of mu z, and therefore when you shoot the electrons through the magnet, you're going to get up, straight, down. That's all you have to worry about. Okay, that's not so bad. All right, very nice. Okay, so that's cool. Now, let's do L equals 0. Okay? Let's do L equals 0. So let's say that the hydrogen is in a ground state, right? So hydrogen is in a ground state. L equals 0. Okay, great. So what are the possible values of M? Well, you know, it goes from 0 to 0, right? So it's just 0. Okay? So 0. So therefore, if M is 0, this is a 0, what's mu z? 0. So therefore, what's the force? 0. So what should the electron do in the L equals 0 state? It should just go straight, right? So that's what they expected. You know, that's what everybody expected. And, okay, that's what they expected. But that's why you do experiments, right? To see if things really go like you expect. All right, so that's what they expected. However, this is what they observed. So this is a real photograph, okay? So they expected just a line, you know, but they got woo, right? What in the world does that mean? That means that something's going up and something's going down. Well, how can that be? That's crazy, right? Because mu is 0, so the force is 0. So if the force is 0, how can you get something to go up and something to go down? I mean, that's totally insane. Oh my gosh. All right? Oh man. So now what are we going to say? Well, the only way to resolve this dilemma is to say that the electron itself, acts like a little tiny magnet. So it has an inherent magnetic moment, okay? So what we're saying is, you know, think about an electron. It has mass, yep. Has electric charge, yep. What we're saying now, we're saying it has a magnetic moment. So we're saying it acts like a magnet, okay? And what are you going to say, right? And remember, we know that the magnetic moment is proportional to angular momentum. So if it has an inherent, you know, magnetic moment, it has to have an inherent angular momentum. So we're just saying that another property of an electron, besides mass and charge, is a magnetic moment. An electron acts like a magnet. Okay. Now, when they discovered this, they kind of said, wait a second now. How can an electron act like a magnet? And they realized if you have accelerating charge, you know, like a current in a circle or something like that, it creates a magnetic field. So they said, well, maybe the electron is spinning in some way, and that's creating a magnetic field. But then they did all the calculations, and it didn't make any sense at all. But for whatever reason, they kept the word spin, which was really a shame. So what we say, instead of saying the electron has an inherent magnetic moment, which would have been the better thing to say, they said an electron has spin. Okay? Now, there's only 2 values of spin, right? It either goes up or down. So there's only 2 values of spin. So what they did, they kind of wanted to copy the orbital angular momentum. You know, they just basically use the same equation, all right? So they just kind of used a pattern, you know? So they said the magnitude of the spin angular momentum, which is S, equals h bar square root s plus 1. Does that look familiar? Sure does, right? But they're saying that s is you only get s a half, or it could be minus a half for the direction, you know? So if s is a half, you put in a half and you get h bar radical 3 over 2. All right? So that's the magnitude. And then the direction, same equation as what we had for the orbital angular momentum. We say ms h bar, but ms is plus or minus a half. Right? So most people say spin up or spin down. All right, so ms is plus a half. I mean, it's really plus a half h bar. That means spin up. If ms is minus a half, so this is minus a half h bar, it's spin down. So that's what spin is, okay? Is this clear as mud or what? Here, let's make it even more. All right, so here's just another picture, okay? So you expect, you know, before they discovered spin, they expected just one line in the middle, no force, but they actually saw a line above and a line below. And so, bingo, there has to be something. Spin, okay, spin. So, what does that mean? Well, you know, solving the Schrodinger equation gave us the principal quantum number, the orbital angular momentum quantum number, and the magnetic quantum number, right? This was the magnitude, this was the direction. So these three came from the Schrodinger equation. This quantum number came from experiment. All right? So now we have 4 quantum numbers. So again, this is m sub s. So I always taught you put m sub l here, but Randy Knight doesn't do that. So ms is spin, and see how they just use the same equation, right? So s sub z equals ms h bar, but there's only 2 values, plus or minus half, up or down. So what does it mean? The fact that there's 2 values of ms means that the number of possible quantum states that an electron can have just doubled, right? Just doubled. All right, whatever. Now, here's what's very, very important. Beware! The term spin must be used with caution. Although a classical charged particle could generate a magnetic moment by spinning, the electron most assuredly is not a classical particle and is not spinning in any literal sense. It simply has an inherent magnetic moment just as it has an inherent mass and charge. And that magnetic moment makes it look as if the electron is spinning. It is a convenient figure of speech, but it's not factual. The electron has spin, but it is not a spinning electron. Now, is that the dumbest thing you've read or what? So why do they call it spin? I really wish they didn't, because it's just really misleading, but that's what they call it, all right? They should have just said magnetic moment, right? But whatever. Okay, so there it is, okay? Spin. All right, and don't forget, this did not come from solving the Schrodinger equation, right? It came from an experiment, the Stern-Gerlach experiment. Okay, so, you know, we've talked a lot about the hydrogen atom, right? That's pretty cool. And so what people did next is they started applying this to atoms with more than 1 electron, right? Wouldn't that what you would do, you know? So this is the potential energy, again, between an electron and a proton for hydrogen. All right, so what we want to do for other elements is, well, now we have to be, it's more complicated, right? Because if we have more than 1 electron, we have the potential energies between the electron and the nucleus, but we also have the potential energy between the electron and the electron, right? Okay, now you got to be careful. The electron is attracted to the nucleus, so that gets a minus sign. We always give minus signs to attractive. We've talked about that before. The electron is repelled by the other electron, so it gets a plus. Okay? So here's the potential energy between the electron and the nucleus. Now you notice it's the same thing as we had before, except we put a Z, right? Because Z is the number of protons. All right? So that's fine. You know, that makes sense, you know. We learned this in Physics 220, all right? So it's the same as for hydrogen, except we have a Z. But now we got to do this, right? We have to have some potential energy dealing with electrons repelling other electrons. Okay? So now there's 2 pieces to it. Oh, gee, what are you going to do, you know? And we're just going to say that this is some kind of average. It's just the average, okay, some average potential energy due to all of the other electrons. If there are 3 electrons or 4 electrons, whatever. So it's just kind of average. Now, when you do that, the energy now, look at, what do you notice? See here, for the 2, n equals 2, the energy was the same for the s state, for the p state. But now when you have multi-electron atoms, these energies are different, right? So now, here the energy only depends on the n. Here the energy depends on the n and the L, right? Different, here's the same n, but different L. So for everything else, like I said earlier, besides hydrogen, the energy depends on n as well as L, all right? All right, so there you go. And that's all I'm going to say about that. All right. Let's talk about the Pauli exclusion principle. We sort of mentioned that a little bit when we were doing nuclear physics. I don't know if I gave it the name, though, but anyway. Let's talk about beryllium-9. All right, the atom. Okay, the atom. And let's just see how the electron should be set up. Okay, beryllium has 4 protons, so 4 electrons. Now look we know that they have different spin, right? Spin up, spin down. So this seems to be sort of logical, don't you think? So this is the ground state. So you have 1 down, 1 up, 1 down, 1 up. No, why not, right? You know, they're all in the ground state. Get the different spins, seems logical, should be great. Well, guess what? The data disagrees. Right? The data, this is the data. This is the ground state. Down, up, down, up. What's the deal? What's so great about that? Well, see here, so what Pauli figured out is this one would have exactly the same quantum numbers as this one. This guy would have exactly the same quantum numbers as that one. So Pauli figured out you can't do that, right? You can't have 2 electrons with exactly the same quantum numbers. Another way to say that, you can't have 2 or more electrons in the same quantum state. So you got to do this, all right? I mean, you got to do it. What can you say? Because now every single electron has a completely unique quantum state. And that's what the Pauli exclusion principle says. So here, okay, so I mentioned this term when we did nuclear physics. No 2 fermions. A fermion is a spin half particle, like an electron. No 2 fermions in an atom can exist in the same quantum state. They cannot have the same quantum numbers. And, you know, and who cares, right? Well, if you're a chemist, you really, really care. Because what does this mean? Sorry, before I answer that question, let's go back to this. So we're talking about atomic structure. You have 4 quantum numbers. First 3, Schrödinger equation. The 4th, the Stern-Gerlach experiment. But now we have this other thing, Pauli exclusion principle. So you really need all of this to understand atomic structure. Okay? Now, what do we use this for? Well, it basically accounts for the ordering of the electrons in an atom. So it really accounts for, I didn't want to see that. Doggone it. That's all right. All right. So here's lithium, right? 3. So down, up. That's it. Next, like that. Okay. So that's just an example of Pauli exclusion principle. Oh yeah. So this is lithium in the ground state, right? 1, 0, 0, plus or minus half, and 2, 0, 0, a half. So this is, okay. Now we can excite this poor little guy, right? So this is the excited state. So this is the lower energy state. This is the higher energy state. So this is excited, okay? So instead of having L equals 0, you have L equals 1. Yeah, enough. Well, I wanted to say the ordering of electrons accounts for the periodic chart, right? Periodic table. So that's pretty cool. I guess I got to do this in gory detail. Huh? Let's quit right now.